Alright guys, so this is going to be our first video in a new little mini unit here. We're still talking about kinematics. We're still talking about moving objects, but now we're going to think about objects that aren't just moving with constant velocity, but we're going to actually move on now to think about objects that are, as you can see here, actually undergoing acceleration. Acceleration is a little bit trickier. This will be a little bit of a trickier unit, or a substantially trickier portion than what we were discussing previously with constant velocity. And for a couple of reasons, there's more math involved, but also I think because this word acceleration in physics, this word has a specific meaning that's different from like the everyday meaning of the word. I think most people in the general public, when they hear the word acceleration, they think of just like speeding up. So, in the general public, we say that to accelerate equals to speed up. And in physics, we would never do this. So a physicist would say that's not good. That's not precise enough. So we're going to come up with a more precise definition, which I'll do for you right now. And what we're going to say is that the acceleration, and I'll abbreviate acceleration with A, is defined as, and I'm going to write this straight away as an equation rather than writing the words out, is defined as change in velocity over time. That is the definition of acceleration. I could put that into words by writing something like acceleration is the rate at which velocity changes. So we can see here the problem with the general public definition is that when we're talking about acceleration in physics, the velocity is changing. The velocity could be going up or down. In other words, the acceleration could be either positive or negative. So maybe I'll just note that right now, that based on this definition, then what we could say is if the velocity is going up, if the velocity is increasing, then that means that the acceleration would be positive. In other words, just looking at this equation, if the numerator is a positive, if the change is positive, if the velocity is going up, that means the acceleration, the whole value of the fraction, is going to be positive as well. In the opposite sense, if the change in velocity is negative, meaning that would mean that the velocity is going down. So imagine if the velocity is decreasing, well, that would mean that you have a negative acceleration. We call both of these acceleration, and you'll notice at no point have I used the word speed. It gets actually complicated when you ask yourself, okay, well, when is the object speeding up or slowing down? And I don't want to get too bogged down in that, but I will mention it later in just a little bit. So before we do that, though, I want to just point out a new type of graph. This will allow us to also make a new graph. New type of graph that I want to introduce right now, and that's the velocity time graph. Do not confuse this with the position time graph that we had last time. So this is a velocity time graph. When we had the position time graph, we put position on the vertical axis. I'm now going to put velocity on the vertical axis, and I'm going to put time on the horizontal axis. Velocity we usually measure in meters per second. Time, again, is in seconds, which reminds me, by the way, that I should go back up here and make a quick note on units. The standard units, this sounds weird, the standard units for acceleration are the units for velocity, meters per second, divided by the units for time, which is seconds. So that means the unit is the meter per second per second. Nobody says meters per second, or maybe they do, but you don't hear it very often. It's usually written this way, meters per second squared. So that's our unit, that's our standard unit for acceleration. So if you hear meters per second squared, that's just meters per second per second. What does that mean? Just to kind of give us some intuition. Let's imagine if the acceleration were equal to positive 2 meters per second squared. That means every second that goes by, the velocity changes by 2. So if we started off, if we made like a little table here, we could say at t equals 0, 1, 2, 3 seconds, what would the velocity be? Well, assuming it starts from rest, after 1 second, it would be moving 2 meters per second. And just, I'm doing this, sort of informally, but just so you're clear on what I'm doing here, I'm using this equation over here. I'm just writing v, or delta v equals a times t. I've just rearranged that equation. So after 1 second, it would be going 2, assuming it starts from rest. After 2 seconds, then it would be going 4. And after 3 seconds, it would be going 6 meters per second. In other words, the velocity is changing by 2 every second. That's what that would mean. All right. So going back to our velocity time graph. Now, in our previous unit, when we had constant velocity motion, we'd have problems where it might be some, I'm not going to write it out, but it would be something like, I think we had one where we had an object was moving in one direction at 10 meters per second, and then it turned around and went the other way at 4 meters per second. So what would that look like, just to get a sense for what in our previous unit, what that would look like on a velocity time graph? Well, if the object started off moving at 10 meters per second, that would mean that over time, the velocity remained 10 meters per second. So we would have a slope, or we would have a line with 0 slope here. And then the object, if it turned around and immediately was going in the opposite direction, so now negative at 4 meters per second, I'd need to have negative 4s down here. What would happen is the object would just like instantaneously, all of a sudden, be moving with a velocity of negative 4, say like that. Again, 0 slope. Now, why am I emphasizing the 0 slope? Because the velocity isn't changing, so that means that as time goes on here, the slope has to be 0 because the velocity is remaining at 10. And down here, same thing, the velocity is remaining at negative 4, so the slope has to be 0 because there's no change in velocity, right? If up to this equation again, if the delta v is 0, then the acceleration is also 0. And it might be worth just noting right away here, what we've just sort of alighted upon is the fact that the slope on a velocity time graph is equal to the acceleration. Don't get confused here. In the previous unit, on a position time graph, the slope was the velocity. But this is a velocity time graph, and on a velocity time graph, the slope is the acceleration. Very, very easy to get confused between those two. Now, I'll just point out something here. In the previous unit, we had the object suddenly going from positive 10 to negative 4 meters per second, as if there was no time in between these 2 points. And looking at the graph from your math class, you probably recognize this seems sort of problematic. How can the object have a certain velocity at one instant and then an instant later be going with a different velocity? In other words, the slope of this line can't be infinite, right? It can't be a vertical line here. Otherwise, it doesn't seem like it would be possible, and indeed it isn't possible. And in fact, the acceleration we're going to see all about, like, how do you connect 2 points in the real world. I just want to point out that that's what a velocity time graph would look like for situations of constant velocity. But maybe we don't have that. Maybe we have a more realistic scenario. I'll just erase this, where we do have an object with an acceleration. So I'm trying to get rid of as much of this as I can, as neatly as I can. So back to this, like that, and that, and that. Okay. So what would this mean? Maybe I'll just sketch a graph and we can try to decide what this would mean. Start here, and I'll go like this, up and then flat. So what would this mean? Well, taking a look here, right here, what does this mean that I started at the origin? Well, it doesn't mean that the position is 0. All that means is that the initial velocity, the initial is 0, meaning the object started at rest. And then after some period of time, however long that is, the object has now, what has happened between these two times? Well, the velocity has increased to some value, and maybe we'll just make some numbers up so we have some numbers to talk about. Maybe I'll call this 6 meters per second. And maybe this time here we'll say is 3 seconds. So what happened? Well, the velocity of the object went from 0 to 6 in a total of 3 seconds. So it accelerated, the velocity changed. And in fact, we could find out the acceleration here. Going back to the equation that I introduced earlier, I could say that the acceleration then, and thus the slope here, the slope, which is the acceleration, would be 6 over 3, which is positive 2 meters per second squared. And then what happens after 3 seconds? Well, here, what does this mean? This means the velocity simply remains at 6. So the object accelerated, and then it stopped accelerating. The acceleration here is 0, because the slope for this straight flat line segment is 0. I'll note right away, at no point will we in this course deal with curved lines on this graph. And that gets back to this notion here, which I sort of omitted before. We're going to be dealing in this course, in this unit, with uniform acceleration, meaning that the acceleration is constant. We will never have changing acceleration. We'll never have curved lines on a velocity time graph. All right, well, maybe just to keep going a little bit, we'll imagine, what if this line continued on? I'll do it in a different color now. Maybe I'll do green. What would happen if we continued on from this point right here, and now we had, and maybe I'll just say that this time here is 6 seconds, and now I'll draw the line starting from this point going down like so. And we'll say that this time here is, I don't know, let's make that 5 seconds. And then down here we'll say that this is, oh shoot, that can't be 5 seconds. It's gonna be 7 seconds. Sorry. That time, make that 7 seconds. And then we'll make this time here, I don't know, 8 seconds. So what is this line segment now? What's going on in this line segment? Well, the slope is negative. That means that the acceleration is negative. And what does the acceleration negative mean? Well, it simply means if the acceleration is negative, the slope is negative, the velocity is decreasing. So first, it goes from 6 down to 0, and that takes 1 second for it to go from 6 to 0. And then it doesn't stop and stay at 0. What does this point mean? Well, this means that the velocity goes from 6 down to 0, but then becomes negative. In other words, at this point right here, and I'll write this out, at this point right here, the object turns around, changes direction. Change of direction from positive to negative. Okay, so this is a pivot point right here. The object is moving in the positive direction here, and then into the negative direction down here, and maybe I won't write that here. I'm just going to note that anytime you're up in this first quadrant here, this is the world of positive velocity, and anytime you're down here below the t-axis, below the horizontal axis, you're in the land of negative velocities. So this is the change in direction where the velocity goes from positive into negative values. So here we could say the velocity is decreasing because it's going to 0. And here we would say, by the way, maybe I won't I'll do this here. Right here, the velocity is decreasing in the sense that it's going from 0 to negative values. And since negative values are smaller than 0, the velocity is still decreasing. So maybe we could go ahead and say, all right, well, what's the slope here? Well, if the velocity goes from 6 to 0 in 1 second, then the slope here, the acceleration, the slope has to be negative 6 meters per second squared. And from that information, by the way, we could also glean if this is 1 second, that this final velocity here has to be -6 because it's another second. So this is -6. So then overall, what we have for this object is it starts from 0, it accelerates to a speed of 6 meters per second, travels at a constant speed of 6 meters per second, and then what happens is it slows down, here's a change in direction, and now it goes in the opposite direction. Now you heard me say right there moments ago, you heard me say slow down. I don't want to get too hung up on this, but I'll just mention, since you people are familiar with the word speed, you do have to be careful when you're talking about speed here, because speed is never negative. So the smallest the speed can be is right here, 0. Right here where the speed is 0, that's the smallest the speed can be. So what you actually have in this section right here, the object is slowing down, but in this section right here, the object is speeding up. It's speeding up because the object is going away from the 0 point. Above the t-axis right here, it's going towards the 0 point, but here it's going away from 0. So here we would say it's slowing down right there, and we would say it's speeding up right here. And that's a little bit weird because the acceleration is negative the whole time. And this is only to say that you can't assume that negative acceleration means the object is slowing down. However, what can we say? We do know that negative acceleration means the velocity is decreasing. But the velocity can decrease, as we saw right here, the velocity is decreasing, but the speed is increasing, which is strange. Don't want to get hung up on that. I think this is enough for one video.